Hi guys, welcome to video lecture number 3, HR diagrams. Today we're going to talk about probably the most important graph in astronomy. Last time we talked about the life cycle of stars, how they're formed, how they expand, and how they die. Today we're going to talk about how they're classified on a Hertzsprung-Russell diagram. The stars in the universe are not all the same. Some are really huge, and others are relatively small compared to them. Some are extremely hot and others burn cooler. Some emit great amounts of energy and others less. Stars may be young, middle-aged, old, or dying, as we saw in the last video. They can be composed mostly of hydrogen, or they may contain heavier elements like helium if they're at the end of their life cycle. Some are very bright, others are dim. Their colors range from blue and white to yellow and red. In the early 1900s, Danish astronomer Ejnar Hertzsprung and American astronomer Henry Norris Russell developed a way to classify stars according to their luminosity and their temperature, which is related to their color. This relationship is shown in this graph. It's called a Hertzsprung-Russell diagram, or HR diagram. On the HR diagram, the stars are plotted along the bottom axis here by increasing surface temperature, which is measured in units called kelvins. Notice that unlike most graphs, the x-axis increases as you go from right to left. Hotter stars are plotted on the left-hand side of the diagram, and the cooler stars are plotted on the right. Stars are plotted along the y-axis like an ordinary graph, in order of increasing luminosity. Brighter stars are plotted at the top of the diagram, and less bright stars are plotted at the bottom. Luminosity is represented here in base tens. Stars along the 10 to the second power tick mark are 100 times brighter than the sun. And stars down here at 10 to the negative 2 tick mark are 100 times dimmer than the sun. As stars increase in temperature, their color changes. The coolest stars are red, and as you move left, stars get hotter and their color changes from red to orange to yellow, then white, and the hottest stars are over here. They are blue. Usually we think of red as hot and blue as cool, but just like the x-axis, the colors are backward on an HR diagram. Blue hot is literally hotter than red hot. Looking at the x and y axis, we can break the HR diagram into 4 quadrants. The lower right corner contains the coolest, dimmest stars, like these red dwarfs. These stars are still incredibly hot, don't get me wrong, but compared to other stars, they're relatively cool. The lower left corner contains stars that are hot but dim. The right upper corner has stars that are cool and bright, and the upper left corner contains the hottest, brightest stars. Several patterns begin to emerge when stars are plotted according to their temperature and their brightness. Stars fall into several categories. Most stars are part of the line right here that is formed from the lower right-hand corner of the graph to the top left corner. They're known as main sequence stars. We've already discussed them in class. These stars are relatively young. They are formed from nebula and are in the longest stage of their life cycle, fusing hydrogen into helium at their core. Notice that as a main sequence star's temperature increases, the trend is that its brightness increases as well. That's why we get the line moving up in this direction. Once a star has no more hydrogen to fuse, it reaches the expansion stage of its life cycle, expanding ever larger, and becomes a red giant. It moves over to the upper right corner of the diagram. When a star runs out of hydrogen to fuse, it cools down, and it begins to fuse heavier elements. But its larger size gives it a greater brightness, even though it cools. Notice that all the brightest stars, the ones at the top of the HR diagram, are really big. The blue giants are hot and bright, and the red giants are cool and bright. The two trends associated with a star's luminosity, or brightness, are these. The larger a star is, the brighter it tends to be. The hotter a star is, the brighter it tends to be, at least for the main sequence, which accounts for 90% of stars. The age of a star can be determined by its position on an HR diagram. Main sequence stars are the youngest. Red giants and supergiants are older. They have already expanded after fusing all their hydrogen. And over here, the white dwarfs are the oldest stars on the diagram. They burn hot, but they're dim because they're the dead core of an average mass star that's already died, as we discussed in the last video. If you ever do a Google search for HR diagrams, it becomes apparent very quickly that not all HR diagrams look completely the same. So I want to show you some other things that you may encounter and explain what they mean. As I said in the last slide, the y-axis represents the brightness of a star. Most HR diagrams measure that brightness in luminosity. Those solar luminosity units measure a star's brightness in relationship to the sun. But you may also see on the y-axis absolute magnitude as a measure of brightness. Whether it's luminosity or magnitude, you need to remember that the y-axis represents the brightness of a star and that it increases as you go up the HR diagram. If you remember that the y-axis is for brightness and that it goes up as you move up the diagram, then it really doesn't matter whether they've graphed it using absolute magnitude or luminosity. Another thing that you might encounter on HR diagrams are colors and spectral classes along the x-axis. You may not always see temperature written out for you by the axis, and you may not have actual numerical values for temperatures of stars. Instead, you might see these spectral classes O, B, A, F, G, K, and M representing the hottest and coolest stars. The spectral classes are a little bit confusing. They're not even in alphabetical order thanks to history. But again, if you simply recall that the x-axis is for temperature and that it increases as you go to the left, you should be fine. The main thing that you'll be expected to do on an HR diagram is to describe stars. So let's take a look at the three examples written below on the slide. First of all, how does the sun compare in brightness and temperature with other stars? So the sun is right here on our graph. Its temperature is hotter than many stars, but it's also cooler than the stars off to its left. In many ways, we can describe its temperature as just being average. Likewise, its brightness is also average. Many stars are dimmer than the sun, and many stars are brighter than the sun. So the sun is kind of a good middleman. Its average temperature and average brightness are easy to compare to other stars. For example, a star that is hotter and dimmer than the sun would be a star that is found to the left as we increase temperature and below the sun. All of these stars, Sirius B, Procyon B, are dimmer than the sun because they're lower on the graph, but they're also hotter because they're off to the left. A star that is brighter but cooler than the sun would be up and to the right. All of the stars above the sun on the graph are brighter, but only the stars to the right of the sun are cooler. Remember, as you go to the right on the x-axis, the temperature drops. So Betelgeuse, Antares, Aldebaran, we could name many stars that are cooler than the sun. So keep your eye on the axis if you're asked to describe stars. Remember that brightness increases as you go up and surface temperature increases as you go to the left. If you look at the axes on the graph, describing stars is no problem at all.